Hi, good morning. I hope you had a nice weekend. Are there any questions before I start? So let me just remind you that today is the deadline for the assignment one by the end of the day. Make sure you submit your assignment. Let's start with another meta theorem that is used quite often. It's splitting merging hypothesis that tells us if you have formulas A, B, C, and a set of formulas gamma, then if gamma union two formulas A and B proves C, then gamma union A and C is a single formula, proves C, and vice versa. So this is an if and only if, and it tells us that we basically can merge two individual hypotheses into the conjunction of them, and vice versa, and we are basically able to prove the same results. Now, the proof is obviously, because the statement is if and only if, is going to consist of two different directions. The forward direction would be when you assume this is true, and then you prove this. So let's assume gamma union two formulas A and B proves C. Now we want to show that gamma union the single formula A conjunction with B proves C. And that means we need to write a gamma union A conjunction with B proof for C. And here is one. Well, before I start writing the first step, I'm actually going to write finitely many steps. I'm going to write all the formulas that are in gamma. So in your textbook, this is denoted by, let me write with another color. Step one. This is denoted by gamma squared, well, inside a square. What is this? It's a notation that we are using just to denote that those formulas in gamma that are used in this proof, right? So here, this is the finitely or the finite set of formulas in gamma that are used to prove are used in A gamma union A B proof for C. Right? Because we are assuming this, right? We know that from gamma and the two hypotheses A, B, there is a proof for C. Any proof is finite, right? That's by definition of a proof. It uses only finitely many steps. So any proof can use only finitely many formulas from gamma, right? And then maybe we also use A and B, but let's call those formulas in gamma that are used in this proof, those hypotheses, like C1, C2, Cn. We don't know how many, so let's call them n many are used. And they all belong to gamma. So these are exactly, I could have written C1, C2 in the infinitely many steps. I could have written it like this, right? C1, C2, and Cn. And this just notation that we are using the square, the gamma inside the square, is just the C1, C2, Cn. Right? We'll just instead of writing n many steps, let's just write it like this. All right, what is in the next step? We also have, note that we are writing a gamma union A intersection as a conjunction with B. So this is a hypothesis. Step 2, hypothesis. Step 3, we proved the theorem last time. I think towards the end, that A and B proves A. So by transitivity, because we have A and B, we can conclude A. Now, step 4, we can also conclude B. The symmetry of A and B allows us to write it as B and A, and the same shows that this proves B. And we already have A and B, so we can also conclude B. Now note that we have written all the formulas from gamma, those C1, C2, Cn, that are used in this proof. We also have written A and B. Now we can conclude by transitivity, we can conclude C. Even if I skip this part, step 1, and I apply transitivity, the proof is not wrong, but this is just more clear, right? Step 5, we can conclude C, and the reason is because, or from, gamma, from our assumption that gamma union A, B proves C. And note that now we have given a C, gamma union A and B proof for C. Here's the conclusion. Now for the other direction, proof is similar. Now assume A union A conjunction with B proves C. We want to prove that A together with two formulas, A and B, can prove C. Step 1, again, consists of finitely many steps. Those are the formulas from gamma that are used in a gamma union A conjunction with B proof for C. Step 2. Again, now we are writing a gamma union A, B proof. That means A and B are hypotheses. So A is a hypothesis. B is a hypothesis, so we can write them down. Now we also proved last time that A and B, they prove a conjunction with B. So by transitivity, we can, since we have both of them, A and B, they're written. Therefore, we can write the conclusion. Step 4, A and B. Note that when I say transitivity, I mean transitivity proof, right? Every time we are doing these kind of arguments, sometimes I may not even say we are using transitivity of the proof, but every time that we use a theorem that we have already proved in another gamma proof, we are in fact using the transitivity of the proof. That is one of the method theorems that we learned, I think 2 weeks ago already. So here, for example, now we have A and B, and we know A and B together, they prove this. The transitivity of proof allows us to prove this directly, or to be able to write this directly because we already have A and B. Any questions? All right, that's for splitting and merging two formulas, but by induction on natural numbers, you can actually do the same thing for any finite number of formulas. That is, if gamma union bunch of formulas imply C, then gamma union conjunction of those formulas implies C or proves C, and vice versa. So anytime when you have a hypothesis, you can take the conjunction of them and have the new hypothesis. And vice versa, meaning if you have conjunction of a hypothesis that is a conjunction of few formulas, you could split them. So this is why it's called merging and splitting and merging hypothesis, right? If you merge your hypothesis, or if you split the conjunction, you basically your proof ability doesn't change. All right, now let's prove one of the most famous rules of inference. Here we did not take this one as a rule of inference, but after proving it, we are able to use it just like any rule of inference, like Leibniz or equanimity. Modest ponens tells us that if you have A and A implies B, then you can prove B. Just like tautological implication is true, right? A and A implies B tautologically imply B. But how do we syntactically prove this in our proof system? Let's start with, I'm going to write an equational style proof. Let's start with this, and then I'm going to use hypothesis A and show that with the hypothesis A implies B is equivalent to B. Note that A implies B is not in general equivalent to B, but it is if A is true. A is equivalent to top, as you will see. So let's start with A implies B. I know this is equivalent to negation of A or B. This is an absolute theorem that we proved. These two are equivalent. Now I know A is a hypothesis, right? So because the hypothesis A is equivalent to top, and this is how we used hypothesis in an equational style proof. Any hypothesis is equivalent to top. So we can replace this A with top because it's equivalent in this proof. So how do we do that? You call this P, use Leibniz, and you replace it with top. So Leibniz, I would write A as a hypothesis. I would write in bracket also what it means. I mean, you don't have to, but just to be more clear, that means A is equivalent to top. What is the C part? C part is negation of P or B, P fresh. That allows me to get negation of A, no, sorry, negation of top or B. But we know negation of top is equivalent to bottom, something that we proved last time. So here I can get bottom or B. How do I do this? Negation of, I want to replace negation of top with bottom. So let's call this P and apply Leibniz. The formula is negation of top is equivalent to bottom. That's the formula that we are using. Now we say, what's the C part? C part is the formula P or B, and P is supposed to be fresh. We also proved that bottom or any formula is equivalent to the formula itself. So this is B. I can just write absolute theorem, right? This is an absolute theorem that we proved. So again, let me see what we did here. We started with this formula, and this shows that A implies B is equivalent to B, right? This proof. But you need to be careful. Just A implies B is in general not equivalent to B, but if A is equivalent to top, then it is. You could also think about it semantically. If A is always true, the truth value of A implies B is same as the truth value of B. If B is true, then A implies B is true implies true, which is true. And if B is false, then the truth value of A implies B is true implies false, which is false. All right, so now we have mod exponents. We can use it in the future. Another useful theorem is the cut rule. that is actually quite a useful one in writing. Once we have it, we can use it a lot to prove more theorems. A or B together with negation of A or C. Again, these are for any formulas A, B, C. These two hypotheses, they prove B or C. And this is called the cut rule because, as you can see, once you have A and negation of A, both in disjunction with some other formulas, then is this basically like canceling A and negation of A, and what remain is B or C. This, hence the name, right? Cut rule. You're just cutting those parts. All right. So in order to write the proof, you could already start with either equational or Hilbert-Starr proof, but sometimes it's easier to argue a little bit and establish few equivalences and relative theorems, and then write the proof. I mean, this is again, is this your choice, but sometimes arguing a little bit before might shorten the proof before writing it. So, for example, here, first of all, we note that negation of A or C is equivalent to A implies C. And we already know that A implies C by an axiom of introduction of implication is equivalent to A or C is equivalent to C. Therefore, by the transitivity of by implication or equivalence, we have this. We actually already mentioned this as an individual absolute theorem, but just to remind you where we got this, this is just a consequence of the axiom and the most useful absolute theorem that we have, this one. So since this was one of the assumptions, this is now a relative theorem, right? And this is the theorem that comes from the hypothesis negation of A or C. So I'm allowed to use it by equanimity, right? Because this I can write in step one. This is an absolute theorem. Then I can write by equanimity. I can write this. But this is a relative theorem that we get relative to this hypothesis, right? Relative to this hypothesis. That means this negation of A or C using one-step equanimity implies A or C is equivalent to C. Now we can replace A or C with C anywhere if we need it in the proof, and we are going to need it here. Let's start with our conclusion, B or C, and write an equational style. B or C, we just said that with these hypotheses, C is equivalent to A or C. So I can use a Leibniz and call this P here, take the C part to be P or B, and replace C with A or C. And this is what we get. Note that in annotation here, I wrote relative theorem. It's just that with these hypotheses, two hypotheses that we have, A or C is equivalent to C. Now, just use the axiom of associativity and transitivity, or both axioms. You can write this as I guess first you want to put the brackets here and then swap them. But we usually said we don't really write the details. This actually applied twice, once associativity and then commutativity of the disjunction. And then that means you can just shuffle these A or B or C in any order you want, put the brackets anywhere you want, right? So we get this. They're the same. Now, A and B is a hypothesis. It's the one that we haven't used yet. So I can replace it with top. So let's call this P. Use Leibniz. The C part is P or C. Or P is fresh. I didn't write in any of these P. P is fresh. P fresh. P fresh. And that allows me to get top or C. Top or C is equivalent to, let me just say this last one. Top or C is equivalent to top. Any formula or top is equivalent to top. This is an absolute theorem. So our conclusion is equivalent to an absolute theorem. Therefore, it's not an absolute theorem, it's a relative theorem because we use hypothesis. This is a relative proof relative to these two hypotheses. Any questions? Yes. A or B is, sorry, you said A or B? Where did I say A or B is equivalent to top? Here, but it's a hypothesis. And any hypothesis from gamma in a gamma proof is equivalent to top. Right? That's the consequence of redundant truth. A hypothesis just you assume you're given that you're assuming is true. That means you're assuming it's equivalent to top. So another remark about this transitivity and using the relative and absolute proof, absolute theorems that we prove along the way is really about the transitivity of the proof that allows us to use all the absolute theorems and relative theorems such as mod exponents and cut rule in our future proofs. All right, I think I've explained that enough many times. Let's get a few corollaries out of the cut rule. First of all, again, let me write what cut rule was so that we have it in front of us. If you have A or C, and you also have negation of A or B, then you can prove B or C, or here in this case C or B, doesn't matter, they're equivalent. First of all, notice that if I take the conjunction of them, the proof still holds by the splitting and merging hypothesis, right? If you have two individual formulas, you could take the conjunction, and the merging splitting hypothesis tells you the same thing. So, but that's not what we are doing here. Now, what happens if B and C are the same formulas. So C is same as B. Now A or B, in negation of A or B, you get B or B, which is equivalent to B by an axiom, the idempotency of conjunction. So we get this. So again, this is cut rule because you're basically cutting A in negation of A. Another corollary, if you have A or B and just negation of A, then you can prove B. Another different, we can write basically different proofs for all of these theorems that we are proving. But here, well, I've written here an idea that negation of A proves negation of A or B. Why? Because we have already proved it. We have proved that for any formula A proves A or B. This is for any formulas A or B, right? Once you have A, then you have A or B, no matter what B is. And also, this is true for any A. I can apply it for negation of A. So we have this, and we know negation of A is one of the hypotheses. Therefore, again, by applying the transitivity of the proof, we get, we can use this as a relative theorem, again, relative to this hypothesis. Now let's see, we want to write either equational style or Hilbert style. I don't think there's a difference. So let's see what's the best way to do this. We want to either start with B or start with one of these. Maybe start with this. Let me have the strategy here. Negation of A or B, since it's a relative hypothesis. No, I think, okay, this would be a lot easier if I wrote a Hilbert style proof for this. Yeah. So step one, hypothesis, A or B. Step two, I mean, I could write the hypothesis here, negation of A, and then do two steps and get negation of A or B, because by transitivity, we can apply this since we have negation of A. Or I just argued here that I can conclude this from the hypothesis. So A, negation of A or B, I'll just here write relative theorem. Now apply cut through. You can get E. Note that I applied this cut rule. It's a consequence of, it's a corollary of cut rule. I'll just call it cut rule again. There's no reason to give different names to these ones. Yes. Sure. So wait. So A is equivalent to bottom, okay, and then what? Yeah, yeah, sure. That's another way to do this. So here's another suggestion, not to use the cut rule. Negation of A is a hypothesis, meaning negation of A is equivalent to bottom. Then from here, you want to conclude, top. You want to conclude that A is equivalent to bottom. First of all, how do you get from here to here? A few steps. It's not trivial. We never did this, right? I never proved this. You need to apply. I mean, I'm not saying this is quite easy. It's gonna take 3 steps to write this, at least. So it's not the short. It's not as short as this proof, but it works. This is, for example, you could replace. I mean, I will leave this as exercise for you to prove if you wanted to use this. How do you prove this? You're going to apply axiom of introduction of negation or redundant truth, but it's quite easy. Or actually, yeah, top versus bottom could be also useful. So this is exercise for you. But once you get there, then you can write here A is equivalent to bottom. So you replace A with bottom and negation of, we started from, hold on, we actually don't need that because we could use this with top. Okay. And then we have top or B. This equivalent to top. This wouldn't give us B, right? So that's the problem. We need to apply this. We basically have, right, you want to replace A with bottom, then bottom or any formula would be same as the formula. So you get B. That's another way to do it. Or you apply the cut rule and you get B. All right. Any other questions? Another corollary of cut rule. If you have A, a negation of A, then you can prove bottom. Well, I've written already one proof for this, method 1. What I want to emphasize here is that really there are different ways of proving theorems. And one way to do it is to write arguments like this that are based on the things that we proved already. We just say we proved this and this implies this, by transitivity we get this, right? That's the correct proof. Or we write a Hilbert style or equational style proof. Sometimes you could mix the arguments, just write few lines and establish some relative theorems, and then write a Hilbert style or equational style proof. So these are acceptable proofs, and it's your choice what you want to use. So here, for example, one proof for this, we have we have this absolute theorem that A or bottom is equivalent to A. We also have negation of A or bottom is equivalent to negation of A. Since we have negation of A and A, that means we have both of these, right? We also have the cut rule that tells us A or bottom and negation of A or bottom, they prove bottom, right? So these two prove bottom, but we know that this is equivalent to A, this, and this is equivalent to negation of A. So A or negation of A prove bottom. There are a few equanimities along the way. Or we'll just prove it. Perhaps it would be more clear if I wrote a direct proof for this. Let's see how we continue here. Well, we have both A and negation of A. We want to get bottom. I know if I start with negation of A, then similar to the proof that you suggested, because A is equivalent to top, because it's a hypothesis, I could replace A with top, and then negation of A would be equivalent to negation of top is equivalent to bottom, right? That's actually not the best way, perhaps even the best way to prove this. Or no, maybe not. That one could be a little bit different. But anyways, so the idea is to write an equation style proof and replace A with top. Why can I do that? Because A is a hypothesis, so it's equivalent to top. Or I'll just write A is equivalent to top. i.e. A is a hypothesis. Now the C part, I'm replacing this. So C part is negation of P. P is fresh. Do I even need to say P is fresh here? Actually, I don't think so, because A is the one that I'm substituting, and there's no other formula than A. We're replacing the top. Here, there's no variable. I don't even have to say P is fresh. Negation of top, we already proved that it's bottom. So this is an absolute theorem. So one of our hypotheses is equivalent to our conclusion, right? Let me just add this extra piece. We don't have to write it every time. I'll just explain again. This shows negation of A is equivalent to bottom. But I mean, as a relative theorem, right? Since negation of A is a hypothesis, we have A and negation of A prove bottom. Any questions? Now the transitivity, yes.
Let me say, does both A and negation of A are both top? That's a contradiction.
Well, when you say that's a contradiction, what do you mean by that? I mean, we are writing purely syntactical proof, right? So you have to give me what are the steps. What axiom or theorem did you use to? So the argument that you're suggesting is that we know that A is equivalent to top. You know that negation of A is equivalent to top, right? That's another proof. But how do we get, I mean, you said this is a contradiction, but you need to be careful. Well, first of all, from the transitivity of the, by implication, you can get that A is equivalent to negation of A, right? But you also have A is equivalent to negation of A is equivalent to bottom, right? Now apply equanimity to step 3 and 4, you conclude bottom. So this is another proof, which is, so this is, I'm going to write it as method 3. So let me write it properly. Step 1, negation of A is equivalent to top, because negation of A is a hypothesis. Step 2, A is equivalent to top. A is a hypothesis. Step 3, A is equivalent to negation of A. Well, I think maybe it's easier to write negation of A is equivalent to A. The transitivity of by implication, right? If two formulas are equivalent to the same formula, they are equivalent to themselves. Now we also have negation of A is equivalent to A is equivalent to bottom. So this is axiom of introduction of negation. In step 5, equanimity using steps 3 and 4, you get bottom. 3, 4, EQN. These are, as you can see, there are a lot of different ways of proving something. Another, yes. For the second method, the conclusion. I mean, here I just said what we did, but notice that we actually don't have to explain it. Here, we started with one of the hypotheses, and we showed that it's equivalent to bottom. And along the way, we used the other hypothesis, because otherwise negation of A is not equivalent to bottom in general. But if A is a hypothesis, then negation of A is equivalent to bottom. So using our hypothesis A, negation of A is equivalent to bottom. That means negation of A is equivalent to one of the hypotheses. And here we already stuck, because the formula that we want to prove, which is bottom, is equivalent to one of the hypotheses. Therefore, we are done, right? It's that would take one equanimity step, right? No, why do you need to show the other hypothesis equivalent to bottom? The other hypothesis may not be equivalent to, in general, to the one that you want to prove. It's not always the case that the conclusion is going to be equivalent to one of the hypotheses, right? Otherwise, we just always write this is equivalent to the hypothesis. But it would be at the end once you prove it, because but they both would be equivalent to top. So whatever you can prove or whatever you can assume is equivalent to top. If you can show that your conclusion is equivalent to one of the hypotheses, you're done, right? That's enough. Or the conclusion is equivalent to anything that we have already proved, absolute theorem or axiom, you're done. But showing that it's equivalent to one of the hypotheses, maybe it's equivalent to A, you can show it. I mean, it is equivalent to A because they're both equivalent to top. But this is funny to say, right? The bottom is equivalent to top. I just said that in this proof, if you have two hypotheses, A and negation of A, then yes, bottom is equivalent to top. And that might sound ridiculous, but well, the hypotheses that you're giving me are ridiculous. A and negation of A. If you give me A and negation of A, I can prove A's bottom is equivalent to top. Next theorem, transitivity of implication. And as the name suggests, we want to show that if A implies B and B implies C, then A implies C. Right? So you just go directly here. We have two hypotheses. Let's write an equational style, Hilbert style proof. Step 1 and 2, the hypothesis. Step 3, A implies B is equivalent to negation of A or B. Step 4, from step 2, I know B implies C is equivalent to negation of B or C. Apply equanimity to both these steps. You get negation of A or B, negation of B or C. In the future, usually it's good to write step 3 or 4. But if you did not, and you just directly went here and skipped the equanimity, it's okay. I would not deduct any points for skipping equanimity steps. But in a Hilbert style proof, usually it's better to write the equanimity step, right? So that we are sticking to the original definition of a proof. Now we have negation of A or B and negation of B or C. And note that here, there's B and there's negation of B. They're both in disjunction with two formulas. The cut rule allows me, I mean, here also, maybe first I should have applied the symmetry and then get B or negation of A. And now they're on the same side. Now I apply the cut rule, but there's no reason for just lengthening the proof with these trivial steps, such as I said, symmetry and associativity. These are the steps that you're allowed to drop. So let's just make that a rule. So we get what? You can cut these. We are left with negation of A or C. The cut rule gives us this, but negation of A or C is equivalent to A implies C. Apply equanimity to steps 7 and 8. Another similar theorem, you have A implies C this time and B implies D. So we have 4 formulas. A implies C and B implies D are the hypothesis, and you want to prove that A or B implies C or D. How do we do this? Well, again, just noticing before that one of the hypotheses A implies C is equivalent to A or C is equivalent to top. right? So this is a relative theorem because I have the hypothesis A implies C by equanimity. I can have the hypothesis. I can have the relative theorem A or C is equivalent to C. Similarly, I can have the relative theorem B or D is equivalent to D. And now that we know in our proof, anytime, because I have this relative theorem, I can replace C with A or C or vice versa. And because I have this, I can replace D with B or D or vice versa. Now let's establish a proof for this. Start with the formula itself. Let's call this E. Let's call this F. You're talking about E implies F. E implies F is equivalent to E or F is equivalent to F. E or F is equivalent to F, right? This is an axiom. Now, notice now that we have these relative theorems, when I say relative theorem, meaning with these two hypotheses, we can prove them, right? With these two, with the first hypothesis, I can prove that A is equivalent, A or C is equivalent to C. And with the second hypothesis, I can prove B or D is equivalent to D. Well, there's just one step proof for any of these, or either of these relative theorems. So, for example, I can take this C or D here, and I know C or, no, it's not C or D. Let's see, what are we taking? B. It looks like I'm taking B or C, but B or C is equivalent to what? Actually, oh yeah, we're replacing B or C with C or B. I was thinking we needed commutativity, but that's what we're doing in the next step, right? So we are using commutativity, call this P, and use the symmetry of B or C. And you see, again, this annotation helped us to realize what we're doing, because there's a P here that suggests that we take this as a P. If we didn't have this annotation in front of us, it would take a while to realize what we're doing here. But this is why we have annotations. So whenever you write a proof in the exam or wherever in the assignments, if I don't have the annotations in front of me properly, I'm going to spend so much time, or TAs would not understand the proof, and you lose some marks. So here suggests that take this as a P and use Leibniz and replace B or C with C or B. And the reason for it is that once we have this, now we have B or D in front of us, and we know B or D is equivalent to D. We also have A or C here, and we know A or C is equivalent to C. So we can replace both of these formulas using two instances of Leibniz. The first one, let's call this P, apply Leibniz, and replace A or C with C using the theorem that we have. A or C is equivalent to C. And then we end up with this. And now B or D, call this P, use Leibniz, and we know B or D is equivalent to D. What we get is C or D is equivalent to C or D. which is an absolute theorem, right? A is equivalent to A. We proved this long time ago that A is equivalent to A is an absolute theorem. So our formula is equivalent to an absolute theorem given those two hypotheses. Therefore, it's a relative theorem relative to those hypotheses. That is, it's A implies C and B implies D theorem. The corollary of this theorem is the most useful, and it says that. All right, let me write this theorem one more time. See, it's if you have A implies C, and you have B implies D, then A or B implies C or D. Now, what happens if C was same as D? Or D was same as C? Now, A or C and B or C imply this. Now, using one step Leibniz, I could replace this with C, because C or C is equivalent to C is an axiom. What I get is this. So if you have B implies C, sorry, A implies C, and B also implies C. So we have two formulas that they both imply C, then we can prove that A or B implies C. Sorry. I'll just sketch the proof, but the details are left to you. But why is this theorem useful? Because it's used all the time in mathematics and even in computer science to prove statements, because it tells us that if I wanted to conclude C, or if I wanted to prove a statement like this, A or B implies C, meaning if A or B, then prove C. Then it's enough to prove these two. Prove this, and then prove this. And you're done. Why are you done? Because these two together, they prove this. So in order to prove this statement of the form A or B implies C, if I prove A implies C and B implies C, then we are done, because by transitivity of the proof, these two, since these two together imply this, we have the conclusion. And often proving these two is a lot easier than proving this. And this is called proof by cases. For example, an application of this would be when you have like statements like A is the formula that says X is divisible by 5. And or X is an odd number, odd integer. And B is the statement that says X is an even integer. You want to show the A or B together means, well, X is an integer. It's either even or odd. So you want to prove that C is true for any integer X, the formula that C is talking about X is true, it's enough to prove two things. First, assume X is odd and prove C, and then assume X is even and then prove C. So this work is called proof by cases, because you could divide your assumption from A or B. If first just assume A and prove C, and then you assume B and prove C, and you have done the same thing, meaning you have proved this. All right. Another corollary of this is when B is negation of A here. Then what do we have? We have A implies C, and negation of A implies C. Together they prove, so B was supposed to be negation of A. Here I have negation of A. So I have negation A or negation of A. They prove C. You know, A or negation of A is an axiom, is excluded middle. So it's equivalent to top by redundant true. And you can also write this using Leibniz, I can have this top or C. Sorry, top implies C. Top implies C is equivalent to negation of top or C. Negation of top using a Leibniz, what? I can replace it with bottom. Bottom or C is equivalent to C. Now just write this, the same thing in an equational style proof using 4 steps. I leave the details as an exercise. All right, now let's talk about one of the most useful. Yes. You replace D with C, but then you get this. If you do that, then you are here. Oh, but that's exact for this or for this one or this one? For the one on top, for this one. But that's what we did, right? That's how you do it. You what you have proved here is for any A, B, C, D. It's not for particular formulas. So you already have, so this is given to you that A implies C, B implies C, proves A or B implies C or C. We have proved this. The proof is here. Now there's just one step equanimity. You just replace C, not equanimity. One step Leibniz. You replace C or C with C. Another very useful, maybe even, well, I can't say it's the most useful method theorem, but one of the most important method theorems that we're going to learn in this course is called the deduction theorem. And let's see what it says. It says that if you have a set of formula gamma and formulas A and B, then gamma union A proves B if and only if gamma proves A implies B. And this is, you will see why it's so important. First of all, okay, we want to try to prove this, even though the proof is a little bit long. We'll sort of sketch the proof. Well, actually going to prove it completely. but in a few steps. First of all, it's an if and only if statement. That means I need two directions to prove. The first direction, let's talk about the inverse, the reverse direction. So what am I trying to show? Suppose gamma proves A implies B. Now, what do we want to show? We want to show that B is a gamma union A theorem. So we write a gamma union A proof for B. Here's the proof. Step 1, A, hypothesis. Note that A is a hypothesis here. We're writing gamma union A proof for B because we want to show this. Step 2, gamma proves A implies B. By strengthening hypothesis, gamma union A proves A implies B, right? So I'm not gonna say I'm using strengthening hypothesis, but this follows from gamma proves A implies B. And we are applying strengthening hypothesis. Now we have one more hypothesis, but one more hypothesis doesn't hurt. Now, step 3, apply modest ponens. Steps 2 and 3 plus modest ponens. So we are done. Sorry, 1 and 2, yes. Thank you. So we are done. So this direction, the inverse direction, was actually very easy. And it's nothing but modest ponens. So one of the directions is nothing new. It's everything that is pretty much obvious. If you have A implies B, and now you have hypothesis A, then obviously you can prove B, and that's what we did. It's trivial, but the other direction is why this theorem is important, is because of the other direction. That how do we prove this? You want to show gamma union A proves B. If you have gamma union A proves B, then gamma proves A implies B. You can try writing the proof for this, but this is you're gonna get stuck if you just go think about this just for a second. You will see that if gamma union A proves B, now how do I write a gamma proof for A implies B? Now A is not a hypothesis here. I'm writing a gamma proof. So what do I do here? You can, for example, write this A implies B is equivalent to negation of A or B, but then so what? A is not a hypothesis. I cannot replace at the top. So what are we doing here? You get stuck. So we need to be creative. The proof is not as easy as the other direction. So we're gonna prove this, and we're gonna even develop a new technique in proving theorems in order to be able to prove this. Another form of induction. But first, a piece of notation. Usually it's customary to write A plus B instead of A union, the single formula So gamma union the single formula B, you write gamma plus A, right? So just gamma plus A means gamma plus the hypothesis A. And we do this only for when A is a singleton here, right? Just a single formula. Otherwise, we'll just write union. All right, first we need a lemma. Note that our goal is to prove the other direction of the deduction theorem. For that, we need a lemma. The lemma tells us that A implies B is equivalent to C proves that A implies in any formula D, replace any variable P with B or replace it with C in the same formula, and the formulas are equivalent. And this is pretty trivial when you think about this, because if B is equivalent to C, then obviously in any formula I can it's a consequence of Leibniz, that in any formula D, I can replace a variable with B or C, I get the same thing. What I'm trying to say is that if I did not this here, this is just Leibniz, right? There's nothing but Leibniz. But we don't know if B is equivalent to C. The thing is, what we know is that A implies B is equivalent to C. Now that this makes this one a little bit more difficult. Now, can I prove that A implies the same thing? The answer is yes, but the proof requires more work. In fact, we're going to prove this by induction on the complexity of the formula D. So the complexity of D, that means the basis step would be to assume D is an atomic formula. That means it's either a variable or it's a constant. For variables, I have two cases. What if my variable was the same P that we are substituting? Or any other variable, Q. So we have to consider this in two separate cases. If D is P, then what do I have here? In the formula P, substitute P with B. What do I get? I get B. In the formula P, substitute P with C, I get C. So what are we trying to prove? We are trying to prove A implies B equivalent to C proves A implies B equivalent to C itself. So the conclusion is the same as hypothesis. So it holds. So if D is P, we are done. Now, what if P was any other variable? If D is any other variable, let's say Q. Now, P is a fixed variable, right? In this one, that's why we consider two different cases in atomic case. P is either the same P or it's a different variable, Q, R, S, T, whatever, right? Now in the formula Q, substitute P with B. Well, you just get Q. There's no substitution done because there is no P in there. Q is equivalent to Q. So what are we proving? A implies B equivalent to C implies A implies Q is equivalent to Q. Q equivalent to Q is equivalent to top. So this is an exercise for you that show that this here is an absolute theorem. Exercise. It's an absolute theorem. A implies, in fact, any formula is equivalent to itself. It's an absolute theorem because I could replace this with top and A. This is top, and then what do we have? A implies top is same as negation of A or top. negation of A or top, any formula or top is equivalent to top. So this is an absolute theorem because it's equivalent to top. Anyways, it's the same if this was bottom. Bottom, you get bottom is equivalent to bottom. So these are done. That's the atomic step or the basis step. Inductive hypothesis. You assume that the formula, this statement is true for formulas E and F. So if you have E, you have this. We are assuming it's true for E. It's the same thing that we want to prove, but instead of D we have E, and also for F. And now you want to show that the same thing is true if my D was negation of E. My D was E or F, E and F, E implies F is equivalent to F. And these last four cases are going to be completely similar. The case that D is negation of E, we want to show this. So this is what we want to prove. Assuming the hypothesis, always our hypothesis is A implies B is equivalent to C. We want to show that A implies in a formula negation of E, replace P with B is equivalent to if you replace P with C. So this is equivalent to, note that the definition, not the definition, we have this absolute theorem that negation of A is equivalent to B is same as negation of A is equivalent to B. So if I take this to be, I haven't said what but by the way, this is sketch of the proof. I did not write exactly what the C part was, but let's see what the C part is. If I take this here, and I call this A, and I call this without the negation B, no, let's call this B. It doesn't matter which one you do first, but this one is what we have done here first. Let's call this A. So now what do we have? A and B already used. Maybe call them A prime and B prime. A implies A prime is equivalent to negation of B prime. Sorry, negation of A prime is equivalent to B prime. Negation of A is equivalent to B prime is equivalent to negation of A is equivalent to B. This is what we get. Negation of A is equivalent to B. And do the same thing for this. Now call this one B prime and call this A prime. Use the same thing. You have A is equivalent to negation of B, which is equivalent to negation of A prime is equivalent to B. Yes. Yes, A prime and B prime. Yes, thank you. So I think we're out of time. I want to stop at some point, but there's one more. I'll talk about this next time. Are there any questions? All right. If not, have a nice day, everyone. See you on Wednesday.